Hello, favorite students. I hope you are enjoying April vacation. I'm glad that you are tuned in to learn about rotation. So we are looking at practice problem number 1 for angular momentum. We are on page 63 of your notes pack, and we're talking about a giant bug on a rotating disk. And because we know we're using momentum, we're going to be using a before and after. And what we might have done when things were moving in a straight line is said momentum before is equal to momentum after. But now we are rotating. We're moving in a circle. So instead of momentum in a straight line, we're going to use angular momentum and angular momentum. So our straight line momentum is P, our angular momentum is L. We used to use mass times velocity. We're now going to use inertia, which is our rotational equivalent for mass, and angular velocity, which is our rotational equivalent for velocity. So what we're going to write here is, instead of mv, we're going to write I omega. So this is angular momentum before, angular momentum after. Inertia is going to be made up of the disk inertia and the bug inertia. So what we're going to do is expand this. The inertia of the disk plus the inertia of the bug multiplied by the angular velocity equals the inertia of the disk plus the inertia of the bug multiplied by the velocity final. Now the inertia of the disk is going to be the same in both situations. The disk does not change. And it actually should have been given in the problem that the inertia of the disk was 450 kilogram meters squared, so 450. What does change is the inertia of the bug, because we know that inertia is equal to mr squared, that's the mass of the bug, and r is how far the bug is away from the middle. So before, the bug was 3 meters from the middle. After, the bug is 1 meter from the middle. So that inertia changes. So what we're going to see here is that we've got 450 as the inertia of the disk plus mr squared equals 450 plus mr squared final. And we're going to take the mass of the bug, which is 10 kilograms, it's a very large bug, and the radius before squared. And we're going to multiply all of that by the angular velocity before, which is 2. Then we're going to take our 450 again, because the disk did not change. The mass of the bug is still 10, but now that radius is 1 squared. And all of that is multiplied by the final. So we have the inertia of the disk before the bug moved, plus the inertia of the bug before the bug moved, multiplied by how fast that bug and disk were rotating. Then afterwards, we have the inertia of the disk again, plus the bug, now that the bug has moved closer and is only 1 meter away, all multiplied by how fast it is rotating after. So if we plug our numbers in here, this is going to give us 1,080 equal to 460 times the final velocity. And when we divide both sides by 460, what we're going to find is that the final angular velocity is 2.4 or 2.4 0.35 radians per second. So when that bug moves from the edge of the disk into the middle, as we can see here, the whole disk is going to speed up. So it's going to be, it was going at 2 radians per second. Now it is going at 2.35 radians per second. So when that bug gets closer to the middle, the whole disk spins faster.